Okay. In this video, we will convert a one-dimensional heat equation solver into a two-dimensional heat equation solver. So first thing I'm going to do, I've saved this as heat 2D, and I'm going to modify an existing one-dimensional heat equation solver. So currently the way that it looks is if we run this thing, we get a nice heat equation showing up here in the plot on the right. And I'm just going to modify this to handle two-dimensional codes. And what we'll see is that we don't really have to mess with our run to kata solver at all. We will only have to modify what's here. So to do that, we'll leave a lot of our time stepping the same, but we'll need different dimensions in space and time. So I'm just going to choose, maybe this will be, so I'll set Lx and Ly. So this will be the length in the y direction for Lx. Maybe we'll say domain length. So we're just solving here on a 2 pi by 2 pi square. And so we have to specify those dimensions. Then we'll also need resolution in the x and y direction. So this will be a resolution, let's say, in x direction. And down here, resolution in the y direction. So this hopefully seems pretty straightforward. Sometimes if I don't want to modify this twice, I'll do something just like nx there. That allows me to change this quickly. Maybe I could call this Ly. So if I want to change my resolution in both directions in the same way, I can do it like this. Normally how I would write that. Notice we've got these little orange underlines here because it's telling us those variables aren't being used, but we can use them right here. So step size in x direction, and we'll have step size in y direction. And since we're doing everything uniform here, we could uniform in both directions. We don't necessarily need to go through all this, but I think it's nice to kind of specify which direction is which, just in case you did want to adjust that later. And so we can kind of see which parts are contributing to which bits. Here we need an x and an y. Okay, so hopefully all of our overlaps. Oh, here I've got a Lx. That should be I don't know why that should be an Lx. Great. Now our orange underlines are mostly gone except for this y variable, which is not being used. And now we need to think about the equation a little bit. So it won't be just uxx. It will actually be uxx plus uyy on the right-hand side. So the double x derivative and then the double y derivative. This is the Laplacian. And maybe we'll even write that. This is nu times the Laplacian of u. So we could think about it as just an xx and a y derivative, but sometimes it's a little bit nicer to think about this as a Laplacian. So not only that, but in Fourier space, we now have two indices. So we'll have not just a k, we'll have k1, say in x direction, and k2. So those will be our variables. You can kind of think about this as a vector-based k. And then here, it will be k1 squared plus k2 squared. Okay, something like that. Now, you might think that we could just do something like call this maybe a k1 squared and a k2 squared and add them together. We might actually call this kx squared and ky squared. But it turns out that that's not going to be enough because this thing, sorry, this should be a y. This thing is a vector, and so if we just say square it and add it to another vector, we'll get another vector. If we square component wise. And what we really want here, this Laplacian object, is if we're thinking about u hat as its values given by for each different k1 and k2, we have a value, right? So its values are given by this u hat. if we think about what type of object that is, that should be a matrix. Although we're really thinking about it not as like a matrix, like a linear transformation, but a matrix is just a table of values. For instance, we could do this also in 3 dimensions, and then we would have sort of a 3-dimensional matrix, or if you like, an array. It wouldn't be any harder though. We would just have here something like a K3 and so on throughout the code. But we'll stick to 2 dimensions for now. If you are going to be doing things in 3 dimensions, MATLAB might not be your best choice unless you're doing things at fairly low resolution. If you start going to higher resolution, you can get in some. It can be pretty costly, basically, to run those things at high dimension, and you probably would want to use a language like Fortran or C++ or some other compiled language, which is going to run a little bit faster. Okay, great. So we've got our K1 and our K, our K in the X direction, K in the Y direction. But now we would like to build this Laplacian operator, and it too will be a matrix. It's got to be, so we've got a matrix here from U hat, and it's got to be multiplied by matrix values. And that is, it's component wise. At each point, it's multiplied by some number. So we have a component-wise multiplication between matrices. Now you can do this with a mesh grid. I find it a little bit easier just to use a loop. I think for me, this is a little more straightforward. It shows you precisely what's going on, and it also translates well to other languages, so that we're not just being MATLAB centric here. So I want to do something like this. Maybe I'll call this Laplacian. Or maybe I'll give it the full name, Laplacian. Can I spell? Sorry, spelled it a minute ago. I'll just reuse that. So I want to have something like Laplacian, and then I need to index it by, say, I, j. So these are just the row and column indices of this thing. And so I'll need to run over I, and I'll need to run over j. So I need a double for loop here, for end. And then one of these should be indexing in I and the other in j. But how do we pick? Well, for something this small, we're doing it only once. It doesn't really matter. But in general, MATLAB will run through the first index first, second index second. This is the reverse of what happens in something like C++, for instance. So here I'm going to run in the first index first. That'll be a little bit more efficient. So I goes, sorry, for I equals 1 up to an x here, and then for j equals 1 up to an y. This type of indexing, indent that. And then for our Laplacian operator, we need to use kx squared and ky squared, but we need to call them according to their appropriate indices. So here, this is the I index, and here, this is the j index. So that's really the difference. Notice that because nx and ny are equal and lx and ly are equal, kx squared and ky squared for this example are actually the same. What makes them behave differently is the way that we are indexing them. Now, this actually isn't quite the Laplacian. The Laplacian is the negative of that. And have I written that? Yeah, so we've got k1 squared, k2 squared, but we want the negative of that. So if I want, oops, just the Laplacian there, I can do something like this. And maybe I'll even pre-multiply by new. We know that we're going to want to multiply by new throughout this whole vector. So maybe I'll call this something like new underscore Laplacian and write it in there. Now, if we run this, let's see, this says variable appears to change size on every loop iteration. So that means that every time we go through this, MATLAB first starts and just declares new Laplacian at 1, 1 as a single scalar, but then the next time through, it needs to grow the loop array. So it will make that a little bit bigger and a little bit bigger. And each time it's doing that, it's copying over the information. This is really inefficient. So MATLAB's prompting us, and we see there should be a little orange bar telling us the same thing, that we should really pre-allocate this. And a quick way to do that is just zeros. and x, y, and y. So this kind of sets up the space. This makes new Laplacian is already a matrix, in this case just a matrix of zeros, and then we're just going to propagate that matrix with the correct values in this loop. Okay, great. So that's our new times Laplacian showing up there, and we're most of the way there. We also need to work on our initial data, so let's find that. We've got initial data right here. But of course, this won't be any good anymore because we now have initial data, which depends on only x. We want our initial data to depend on both x and y, which again will make it like an array. Maybe I should call this something like new Laplacian path, by the way, to make it clear that that's in Fourier space. This is the Fourier symbol of new times the Laplacian. Okay, good. Along the way, we should also change our, this is just based off dx, so we should change our CFL, and we will always want to take the most restrictive condition we can on the CFL. So in this case, let's take the minimum of dx and dy, square that, and divide by nu. Great. Okay, but we'll have to change here our initial condition. So here, we'll do this again with another loop, and it can be a loop over the same indices. Here, we're thinking about these indices running over Fourier space. Here, we're thinking about them running over physical space, but I and j go over the same number of indices, so that's why we see something showing up, which is looking similar there. But u, so by the way, one could do this all with mesh grid. Again, I find it easier just to do it as a double loop here, which secretly is what is happening if you use mesh grid in the background anyway. But I'll let you look into that if you want to look into using mesh grid. Oops, excuse me. So here I'll do I comma j. So u at I comma j. Of course, we should also pre-declare this variable u. So u is equal to this. Maybe we'll say something like set initial condition. So it can be something like, oh, let's do sine of x, but x we need to index, so xi, and then we'll have something like maybe times. We don't need dot times because this is, sine of x at a particular value, so it's not giving us a vector. Maybe times cosine of y, and all the y's will be indexed by j. If we want to put in something maybe higher frequency, we could do, let's do something like cosine of xi times cosine of yj, but let's multiply those by something like, maybe 17 and 13. Some nice prime numbers there. We don't need to use primes, it's just using them for fun. Okay, good. We no longer need this bit. We've taken care of that with our assigning of u and j, but we do need to take the Fourier transform to get into Fourier space. We can still call it u hat, no problem there, but this is a one-dimensional Fourier transform, and if you use a one-dimensional Fourier transform on a two-dimensional array, it will take the Fourier transform in just one direction, I believe, something like that. There is a built-in FF2, or FFT2, which is a two-dimensional Fourier transform, but it turns out it just calls the n-dimensional Fourier transform, which is a compiled code. So I've done several tests on this, and I find that FFTN is the fastest way to go here. So I'm just going to call FFTN directly, and we'll just do it that way. In fact, we should replace all of our inverse Fourier transforms and Fourier transforms with FFTN. And so to do that, we can just do a find replace, FFT with FFTN parentheses. So FFT parentheses replaced with FFTN parentheses. Notice that will also replace all of our inverse Fourier transforms. Video replace all. I guess it's really only it's only in one place. Okay, not a big deal. But it's good to make sure you're not taking one-dimensional Fourier transform circumstances. Okay, great. So after that, this plotting won't work in the same way anymore. First of all, let's plot with kind of a top-down view. So to do that, one nice way to do it is to use p-color. P-color does not have a line width attribute. We'll take the inverse Fourier transform here, and then we'll do x comma y comma inverse Fourier transform. So this is just a color plot. Our x limit and y limit, well, in this case, let's see, I guess we're going with x and y, we're going 0 to 2 pi. Yeah. So we can do x limit 0 to 2 pi and y limit can be 0 to 2 pi. You can set this with a single command axis. We can still look at our title here. So this is just format 1.3, so 3 decimal places to the right, and then looking at time evaluated at that current time. I guess this should really be t at ti there. It's the time we're looking at currently. Great. We'll draw the thing and see how it looks. I think that should go. Oh yeah, of course, we do need to change a little bit here. So when we send in these variables, I guess we no longer need to send in new. We're sort of already pre-multiplying those. So we can just send in new Laplacian hat. Or if you saw my other video on Berger's equation, you know that you can package parameters together in a single variable. But here I'll have new Laplacian hat, and then it's dot times u hat. That's going to be a component-wise multiplication of these matrices. And of course, we need to change the argument up here. So that's new Laplacian hat coming in. Okay, great. Let's see how this goes. If we run it, I think we're going to see, yeah, we see this kind of nasty black stuff all over. It's looking a little bit funny. So we can make that look quite a bit cleaner with a few tricks. So first is to, after we use p-color, we can type shading space flat. And what that's going to do is just right now it's drawing all of the lines in between. That looks okay when you're in low resolution, but high resolution, sometimes there's so many lines in between the various points that you can't see anything. Other options are shading in perp, for instance, which gives you a nice interpolated look. I'll just use shading flat for now. And we get something looking like this. Looks like we're getting a little bit of blow up here. And I think that's because our CFL for this two-dimensional thing is maybe a bit too high. Let's cut it in half. If we run there, we're seeing something that, well, is still maybe seeming to blow up a little bit. It's a little bit hard to see exactly what's going on here because we don't have any scale for the axes. So we don't really know how large these things are. So a quick way to get around that is to use color bar. We run this, see that the axes, we're getting some growth in the modes, and then then there's a strong blow up. Do we have minus in the wrong place, perhaps? Should have a minus here coming out of the plus. We've got a minus here. My k squared already had the minus built in. So technically we're seeing the backward heat equation here, and let's make that a plus because this is kx squared. We built a minus into that already. Let's see if we run this direction. There we go. Okay, so now a much tamer simulation. We have the highest little layer there is missing. So we can use something like axis tight. Axis tight on this. Maybe we won't need the we'll stop there. Maybe we won't need to pre-declare the axes there. Yeah, okay, seems okay. And we're getting this nice axis running. Now, it doesn't really look like much is going on because the axis is constantly rescaling itself. So one way we can deal with that is to type something like c-axis, which is the color axis. And here we can go from maybe, since the heat equation has a maximum principle, it has a fixed maximum and minimum. So let's find those. That is, the maximum and minimum occur at the initial time. So we can do that. We can find those values pretty easily. Let's say something like U max is the max. You can do the max and the max of U if you want. The first max will take the max in one direction. The second max will take it in all directions. It turns out to be a little bit more efficient, though, to do max of U. And then if we write something like that, that'll turn the array that U is into just a single, it'll think about it as a single vector. And then we can just take the maximum of that and the minimum and compute it similarly. So this is U min, and yeah, so we've got our max and min. So our color axis here should be U min, comma, U max. Hopefully that will fix it. Let's take a look. So it's going a little bit slowly, but I hope you can see it. So the color axis is staying fixed now, and this definitely looks like it's fading a little bit. Let's speed up our time step here, a little bit. Now the standard way, or the standard quick way to do this is with just oops, supposed to be mod something like mod ti equals 1, and then end it. That is one way to go. Oh, sorry, if mod ti, so this will make it plot every 10 seconds. So we see now the animation is a lot faster. So that is one way to solve the heat equation in 2D. There are many other efficiencies we could add here, but I just wanted to give you a quick overview of how to update your one-dimensional Fourier code into a two-dimensional Fourier code.